Hello, everyone. I'm Tina, and this video is a walkthrough of my research using convolutional neural networks for multivariate time series. Traditionally, time series were done univariate, as in using just a single series, such as this classic ARIMA example of predicting airline passengers. As I took a look at research on multivariate time series, most were using RNNs and related networks such as LSTMs or encoder-decoders and the like, which take the output of the previous time step and feed it into the next node. Whereas convolutional neural networks are famous for computer vision and image classification. They identify patterns and features relative to the spatial context around them, which actually sounds perfectly applicable to time series, looking at the context of surrounding time points. After all, what really is the difference between a matrix of numbers representing pixel cats versus a matrix of numbers representing prices? Cat? Google stock price? They're like the same thing, right? I mean, they're a little different, but neural networks are a modern and forward past thinking thing. And let's just say my neural network can be open-minded and accepting of diversity. Anyways, when they're not given enough diversity, neural networks may become racist, and we don't like that. Similarly, with color channels, R, G, and B might as well be Apple, Google, and Microsoft. So I took daily data from Yahoo Finance, 5 years of some related stocks, to try to make forecasts on Google's next day stock price. A brain teaser I ran into was whether this model should be 1D, 2D, or 3D convolution. 1D convolutions convolve across just one axis, such as time, and are sometimes used for time series. They take in 1D arrays and output 1D arrays. 2D convolutions convolve both up and down and left and right, generally for images, and they take in 2D matrices and output 2D matrices, and so on the like with 3D convolutions. And we also have 2D convolutions with 3D inputs and 2D outputs. But what was my thing, though? I wanted to put in a 3D input and have it convolve in one direction, which wasn't really one of the options, so I just picked one. I couldn't really think of why having it convolve two directions would make it any worse than one direction, so I went with a 2D convolution. Actually, I also tried 1D, and spoiler alert, it really made no difference at all to the results. And apparently there's a whole area of research about how randomly trying architectures is a good way to go, so I don't really feel bad about just picking one. I created my sample observations by splitting the data into non-overlapping windows of 5 days each. I would have liked to try longer windows, but since I wasn't overlapping my windows, it reduced my number of training observations to very few. I could have used my data more efficiently by letting them overlap, but then that would involve more complicated train test splitting to avoid training data leaking into the test set, and I just didn't want to deal with that for now, so I ended up with windows of 5 days and 250 samples. I scaled the data by dividing each column in each window by the max of it. So for example, the volume column for Google for one sample window was scaled by dividing with the highest volume out of the 5 days in the window. I decided to do that because I realized that with this upward trending time series, if I scaled the whole thing according to the max of the entire series before splitting out the windows, every window would have a different range just depending on how far back in time it was. And the early windows would all have small values, while the later windows would all have large values, which was not useful. Whereas scaling each window relative to just itself brought out more consistent windows that followed apparent patterns. My target was a binary classification of whether the next day's high would be higher than the previous day's high. I also tried a target as the next day's high as a percentage of the previous day's high, but I didn't end up following this train of thought because I found the binary classification more simple to evaluate goodness of the outcome. So the validation accuracy of my model always finished at 58%, which I might call a success considering that it's better than a coin toss. In comparison, I also tried putting in just Google by itself, and it also got 58%. So it seems like the other stocks weren't much help, though maybe if I had picked different stocks, either for the target or for the features, perhaps it could have done better. I also don't know whether this model would generalize well to the future, since past performance is not a guarantee of future results. But that concludes this report. So thanks for watching.